Linearization. Given the function y equals f of x, find the linearization of that function about the point x naught, y naught, where x naught, y naught is some point on the curve. Once you've picked the point on the curve, the linearization is simply the equation of the tangent line at that point to the curve. And as usual, that tangent line is simply given by y naught plus the slope times x minus x naught. And generally we'll call that L of x for the linearization of the function rather than the function itself. So this is the linearization Lx of the function f of x, and it is simply f of x naught plus f prime of x naught times x minus x naught, or y naught plus the slope times x minus x naught. The thing that makes linearization distinct from just the tangent line is usually with linearization we have to worry about how far away we can go from the tangent point before the value of the linearization diverges from the value of the function far enough that we can no longer live with using the line instead of the complex function. The whole point of this is to find a simple function that we can evaluate much quicker and with much less effort than the function itself, which may be some very complex function. This is particularly important in terms of real-time control applications where things have to happen very quickly. So generally, we have a specified maximum error that we can tolerate for the given process we're working on, and we're trying to control the domain of the tangent line, or the linearization over which we allow that line to represent the function before it gets too far out of specifications. So E, we're going to let be the desired maximum error, and we don't want to go above it, we don't want to be too far above it, and we don't want to be too far below it. So one way to conceptualize this is simply if you shift the function f of x up by e and down by e, you've created a band within which, at any vertical line here, the red curve on top is e greater than the black curve, and the lower red curve is e less than the black curve, which gives you the bounds of acceptable error. And then if you can simply find the intersection of this tangent line with the shifted functions to enforce that inequality, that the fact that you want the error, which is the difference between the tangent line and the function itself, if you want that error to meet the specifications, then we can find out what x values we can use this linearization over before we get out of specification. The algebraic statement of that requirement is that the actual error, the absolute actual error, so we don't have to actually look at the function and decide whether we should be looking below the curve or above the curve. We simply want to use the absolute error, and in that case we can, that way we can not have to worry about what the function looks like, but we can just do it computationally. So the absolute actual error is simply the absolute value of L of x minus f of x. It's the distance between, at any given x value, the red curves and the black curve. We want that to be less than the absolute allowed error, which is our goal for not exceeding that amount of error. So this is a zoom in of the function itself, the black curve, the tangent line, the blue curve, the red skinny curves, which are simply the function shifted up and down by the maximum allowable error, and the two little red lines represent the maximum allowable error. The vertical red lines, vertical black lines, show how far from the tangent point you can move in the negative direction and the positive direction from the x0 point before you would exceed the allowable error. As you can see, if you moved a little bit more to the left, the red line between blue and black would exceed the allowable error. So what do we do if we need more of the function than can be satisfied by our constraints on the maximum error? We would simply create a series of tangent line segments, each one of which did not exceed the maximum allowable error. Why would we want to do that? Largely anymore for real-time applications. If you're sitting at your desk working on this with Mathematica, you probably wouldn't need to linearize because you can simply calculate the function itself in most cases in a fairly rapid manner. If you're trying to control your quadcopter, if you're trying to control an engine, applications where you have to make calculations every few small fractions of a second in order to create a correction to something in the next fraction of a second, then you would need to possibly calculate faster than what a very complex function could be evaluated at. And in that case, you could simply create a series of lines which can be calculated very quickly, and all you would have to do is find out where you are along the function, look up between which x bounds you fall, look up the slope and the intercept for that line, and then calculate that with an add and a multiply. Look up for a given point the bounds between which you fall, go into the table, look up the slope and the intercept, and again calculate for the given x point using the line the value of the function. This is a very quick and efficient way to come fairly close to what results you want. The alternative would be to either get a very, very fast processor, or you could purchase a software package which would have the functions you needed. With a simple microprocessor, all you have is essentially add and multiply and maybe some divide and subtract. And then after that, you would have to possibly purchase a software package to load into that, and it might not run very fast if you have a fairly small processor. So the idea of linearization is like a first step at how to make things run fast on simple processors in real time. In practice, the idea of how do you do this is actually an application for a course called numerical analysis, where you can look at the various ways that things might be computed, the trade-offs amongst those. Computer scientists have spent a lot of time figuring out how to do things, complicated functions, very fast. So linearization may or may not be a viable option, but it is a simple conceptual option that we can use here to work some calculus problems.